Hello learners, today we are going to discuss about another machine which is named as induction motor. During my last session on the topic fundamental of DC machine, I have classified machine on rotating basis as DC machine and AC machine. We have dealt in detail about the DC machine, now we will talk about the AC machine. The AC machines are further classified as induction machine and synchronous machine. Among the induction machine, we have induction motor and induction generator. Induction generator is not widely used, but induction motor is widely used for different application right from domestic, commercial, industrial and even for the agriculture purpose. So, this is a very important machine. So, today we will discuss in detail about this machine. Now, let us have an introduction about this induction motor. This is a 3-phase induction motor and is being common and frequently encountered in industries. The reason behind for it being widely used are as follows. First of all, its design is very simple. It is rugged, that is, it can be used for any rough and tough work. Its price is very low, hence economical, and also the maintenance required is very less. In other words, I can say it requires easy maintenance. The second advantage it holds that it is available in wide range of power ratings, that is from fractional horsepower to 10 megawatt. The third advantage it holds, it runs essentially at constant speed from no load to full load, that is to say the variation in the speed from no load to full load is very small, hence for all practical purpose we can assume it to be a constant speed motor. The fourth advantage it holds that its speed depends on the frequency of the power source. So, as soon as the frequency of the power source remains constant, its speed remains constant. Not easy to have variable speed control, it requires a variable frequency power electronics drive for optimal speed control. Now, after going through its advantages, let us come to the construction of this machine. This machine has 4 basic parts. One is called stator, another is called rotor. On the stator, we have a stator winding, and the last and the fourth one is the rotor winding. Now, let us take one by one each part. First of all, we take the stator. As the name suggests, it is the stationary part of the motor. It consists of a steel frame that supports a hollow cylindrical core. Now, this core has the slots on its inner periphery, and moreover this core is laminated. I am again want to remind my viewers that this lamination is being done to reduce the eddy current loss. And on these slots which are being made on the armature core to accommodate the stator winding. The stator winding used is the 3-phase stator winding. Therefore, we have to supply a 3-phase source to this stator winding. The next important part of this motor is the rotor. As the name suggests, it has a revolving in nature, and that is why it is termed as a rotor. It again consists of the lamination which are stacked to create a series of rotor slots. These slots are on its outer periphery of the rotor core, and these slots are meant to accommodate the rotor windings. Now, 2 types of rotor windings are being frequently used, and you will surprised to note that the motors are named according to way the rotor windings are being designed. So, what are the 2 types of rotor windings? Let us take one by one. The first one is the conventional 3-phase winding, which is made up of an insulated wire similar to the winding on the stator. Now, this type of induction motor is known as wound rotor induction motor. Another type of construction is being involved where aluminum or copper bars are being put in the slots of the rotor, and at the ends these aluminum or copper bars are short circuited by copper or aluminum rings. And in this way they form a cylindrical structure which looks like the cage of a squirrel, and that is why this type of motor is known as squirrel cage induction motor. So, viewers, it will be very clear that how these motors are being named. They are being named after the way the rotors are being designed. So, two basic designs depending on the rotor design we have discussed. The first is called the squirrel cage induction motor, where the conducting bars are laid into the slots and shorted at both the ends by so called the shorting rings. Another we have studied is the wound rotor induction motor, in which the three phase windings are wound together to form a three phase structure, and they are being shorted by so called the slip rings. Mind it, these slip rings are same as the split rings used in the DC machine. Now, since additional device called slip rings are being used, the wound rotor motors are costly in comparison to squirrel cage induction motor. Now, you can look to the screen. There are two images are there. One is of that squirrel cage rotor. You can see the shape of the rotor looks like the cage of a squirrel, and that is why it has been named. Now, in the wound rotor induction motor, you can see slip rings are there. Now, these slip rings makes the cost high, and that is why they are being rarely used. One more disadvantage of wound rotor induction motor is that these slip rings require maintenance also, and therefore, the cost is high. And another cutaway section of a typical wound rotor induction motor is being shown. You can see slip rings are also there. In addition to slip ring, brushes are also there, and that makes the cost of the wound rotor machine more high. Now, let us talk about the another phenomena called rotating magnetic field. Now, this is the principle of operation of the induction machine. How a rotating magnetic field is produced? In DC machine, we have seen that a field is stationary in nature, while in this case the field is rotating in nature, and this rotating field helps in the operation of the induction motor. How a rotating magnetic field is produced? Let us see. Balanced three phase windings are there. When I say balanced three phase winding, it means they are not only mechanically 120 apart, but the current flowing through them is also 120 electrical phase difference. So, when a three phase supply is given to a three phase winding, definitely current will flow through each winding. The result of this current is that a magnetic field is produced. This magnetic field will be also three phase in nature. When this three phase magnetic field interact, then it will produce a rotating magnetic field, and this rotating magnetic field will rotate at a speed known as synchronous speed. And this synchronous speed is given by mathematical formula 120 F upon P, where 120 is the constant, Fe is the frequency of the supply source, and P is the number of the poles. Mind it, this synchronous speed is given in the unit RPM, which stands for revolution per minute. So, the conclusion we are getting from this is that whenever a three phase winding is supplied with an three phase current, a rotating magnetic field which rotates at synchronous speed is produced. Also, we can find out the synchronous speed, as we know that the power supply used in India is 50 hertz, but in America it is 60 hertz. So, accordingly we can find out the synchronous speed for different pole configuration. Say for 50 hertz, if there are two poles are there, we have a synchronous speed equal to 3000 RPM. For 4 it is 1500, and this goes on, and for 12 poles we have a 500 RPM. So, the conclusion we are getting that as we increase the number of the poles, the synchronous speed of the rotating magnetic field will reduce. The same case is true for 60 hertz, as can be seen from the table. This can be also explained with the help of the graph. In the graph, the three magnetic flux are being shown, which are in three phase manner. So, what we see that at any instant, say t is equal to 0, we get a resulting flux in this direction. Now, what will happen after 1/4 of time has elapsed, we will see that again the 3 phase fluxes will interact, and now the resulting flux has shifted and it has moved upward. The same situation will happen for another quarter of rotation, where the resultant magnetic flux will be on this direction. For another 1/4 rotation, we will find that now the 3 phase flux will be in the downward direction. In this way, we conclude that this magnetic field which is produced by 3 phase winding is rotating in nature. Mathematically, we can also prove that this magnetic field will be rotating in nature. You can see the 3 flux densities are being taken, and ultimately a mathematical formula has been derived. If you place the value of time t, you will find that this field is rotating in nature. Now, let us come to the principle of operation. We have a stator. On the stator windings are mounted, and these are being supplied from a 3 phase supply. So, definitely they will produce a rotating magnetic field in the air gap. Now, this rotating magnetic field will cut the rotor conductors which are placed on the rotor slots. Initially, the rotor is stationary in nature. Therefore, this rotating magnetic field will react with the stationary rotor conductors. Now, according to the Faraday's law of electromagnetic induction, which state that whenever there is a relative motion between a conductor and a magnetic field, an induced EMF is produced. In DC machine, the magnetic field was constant, but the conductors were moving. Here, the magnetic field is moving, but the conductors are at stationary. Therefore, a relative motion is there, and therefore, induced EMF is produced in the rotor conductors. Now, these rotor conductors are short circuited, therefore, definitely a induced current will produce, and this induced current will produce the rotor magnetic flux. So, there is an interaction, electromagnetic interaction of rotating stator magnetic field and the rotor magnetic field. Due to this interaction, a torque is generated, and this torque makes the rotor to start moving. This torque so produced is a result of interaction of these two magnetic field, and therefore, it is given mathematically by k constant times cross product of magnetic field flux density of rotor and magnetic flux density of stator. So, now the rotor has start rotating. Now, the question arises, at what speed it will rotate? Can the induction motor run at synchronous speed at which my magnetic field is rotating? Okay, so see what happens. If the rotor runs at a synchronous speed, then that is at the same speed of the rotating magnetic field, then rotor will appear stationary to the rotor magnetic field, and the rotating magnetic field will not cut the rotor. So, no induced current will flow in the rotor, and no rotor magnetic flux will be produced. So, net torque will be 0, and the rotor speed will fall below the synchronous speed. Now, as soon as it will fall the synchronous speed, again there will be a relative speed will be there, and that will again produce the rotor current, and thus the motor will start rotating. In this way, the rotor will always slip the synchronous speed. Further, the rotor will always rotate in the direction of the rotating stator magnetic field. Why? The reason behind is the Lenge's law. The Lenge's law states that the induced current flow in such a direction that it opposes the cause. Now, the induced current so produced in the rotor, the cause is the rotating magnetic field. So, the induced current will produce the flux in such a direction that it will try to oppose the rotating magnetic field, and therefore, it will start moving in the direction of the rotating magnetic field, so that their relative speed became 0. But as I have already explained you that this is never reached, the rotor will always slips behind the synchronous speed. And we have also introduced a technical term called slip, because the induction motor will always run at a speed lower than the synchronous speed, and the difference between the motor speed and the synchronous speed is called slip. Mathematically, it is written as n slip is equal to n synchronous minus n rotor speed. We define a term slip, that was the slip speed. Now, we define the term slip. This is a ratio of the two terms. The first term on the numerator is n synchronous minus n rotor speed upon the synchronous speed. This term is referred as slip. If s is equal to 0, it means that the rotor speed is equal to synchronous speed, and if s is equal to 1, it means that the rotor is stationary. Slip may be expressed as a percentage by multiplying the above equation shown on the screen by 100. Notice that the slip does not have any unit because it is a ratio. Now, after dealing with the constructional and operational principle of induction motor, let us talk about the induction motor and the transformer. You will surprised to know that the induction motor and the transformer have some similarity, because both induction motor and transformer work on the principle of induced voltage. Now, what is that similarity? Let us look to these points. In transformer, the voltage is applied to the primary winding that produce an induced voltage in the secondary winding. Similarly, in induction motor, voltage is applied to the stator windings and the induced voltage is produced in the rotor windings. Now, what is the difference? The difference is that in case of induction motor, the secondary winding can move because it rotates, and due to the rotation of the rotor, the induced voltage in it does not have the same frequency of the stator voltage. While in case of transformer, we found that the induced voltage have the same frequency as that of the primary voltage source, but in this case this is not so. So, what is the frequency of the induced voltage or induced current? Let us discuss this. The frequency of the voltage induced in the rotor is given by pole multiplied by n upon 120. What is n? N is the slip speed, which is defined as ns minus nm, and therefore, when we solve it, it comes out to be s into Fe, where Fe is the frequency of the supply source. So, the frequency of the voltage induced in the rotor is slip times the frequency of the source. This is a very important derivation from induction motor point of view. So, what conclusion we are getting? That the rotor frequency is variable and it depends upon the slip. So, when the rotor is blocked, means slip is equal to 1. The frequency of the induced voltage is equal to the supply frequency. On the other hand, if the rotor runs at a synchronous speed, that is slip is equal to 0, then we found that the frequency will be 0. Hence, the range of the slip is between 0 to 1 for an induction motor. Now, after finding out the formula for the slip frequency, let us talk about the torque. The input to the induction motor is electrical, but its output is always a mechanical power, and for that purpose we should know some more quantities. Any mechanical load applied to the motor shaft will introduce a torque on the motor shaft, and this torque is related to the motor output power and the rotor speed, and therefore, the load torque is given by the output power upon the speed in Newton meter, and this speed is given by 2 pi Nm upon 60 radian per second. So, this is also a fundamental concept related to the torque, which will be utilized in the induction motor problems. Another word which is frequently comes while solving the problems related to induction motor is the horsepower. Basically, it is a unit used to measure the mechanical power, but we as electrical engineers deal with the watt as a unit to measure the electrical power. So, we should know the relationship between the horsepower and watt, and this 1 horsepower is equal to 746 watts. So, after going through these terms, we talk about another two phenomena which occurs frequently in the induction motor. One is the phenomena called the crawling of induction motor. Now, what is this crawling of induction motor? First of all, I will give you the definition. The squirrel cage induction motor has a tendency to run at a very low speed compared to its synchronous speed. This phenomena of running at a very low speed is known as crawling. It is expected from the induction motor that whether it is at no load or full load, its speed will be approximately equal to synchronous speed, not synchronous speed, but near to its synchronous speed. But at times it has been found that it run at a very low speed. This is phenomena is called crawling. Now, why this happens? This happens due to the harmonic fluxes produced in the air gap of the stator windings, and the predominant odd harmonics are present, and which are the third harmonic, fifth harmonic and the seventh harmonic. What they do? These harmonics create additional torque fields in addition to the synchronous torque. So, the torque produced by these harmonics rotate either in the forward direction or in the backward direction at a speed ns by 3, ns by 5, ns by 7 respectively. That is, each harmonics will produce its own torque and they will either move in backward direction or in forward direction at a reduced speed. Out of which these three harmonics which I have mentioned, the third harmonics has a very low role, hence it can be neglected for practical purpose. As far as the fifth harmonics is concerned, it has a braking action, that is, it acts in the backward direction, but its role is very small because its magnitude is very small, hence it can be neglected. The dominant role is of the seventh harmonics. This seventh harmonic produce a forward torque which rotate at a speed ns by 7. Now, the torque produced by the seventh harmonics reaches its maximum positive value just below 1/7 of the synchronous speed, and at this point slip is very high. So, what happens? At this stage the motor does not reach up to its normal speed and continues to rotate at a speed which is much lower than its normal speed. This causes the crawling of the motor at just below 1/7 of the synchronous speed, and the phenomena of the crawling starts. Another phenomena which happens frequently in the induction motor is called cogging. What is this cogging phenomena is there? This characteristics of induction motors come into picture when motor refuses to start at all. Though we consider induction motor as a self starting induction motor, but at times it has been found this cogging phenomena happens where the motor refuses to start. Why it happens? The reason behind it that the rotor and the stator slots get locked together, and this happens when the number of the slots on the rotor are equal to the number of the slots on the stator. So, when they face to each other, they get locked because of the minimum reluctance of the magnetic path, and thus motor refuses to start. So, how to remedize this problem? Because this is very important problem. Once motor will not start, our work will not be successful. So, the remedy is that the number of the slot in rotor should not be made equal to the number of slot in the stator. This is the one method. Another method is that the rotor slot are skewed. They are skewed at a certain angle so that they will not directly face the stator slot, and thus the cogging phenomena will not take place and the motor will be self starting. Dear learners, I am summarizing what I have told you today. We have talked about a different motor which is named as induction motor. We have talked about the rotating magnetic field, and then we have utilized this rotating magnetic field concept in the principle of operation of the induction motor. We have also talked about the two important phenomena that take place in induction motor, cogging and crawling. Hope you have enjoyed this lecture. Thank you very much.